Welcome everybody, and thanks a lot to the organizers for putting this meeting together. I will talk about virus dynamics in the presence of contact-mediated host dormancy, and this is joint work with Jochen Blatt, also from TU Berlin. So what is our biological motivation? It has been observed that there are some viruses that attack microorganisms like bacteria or archaea, and one possible defense strategy of the microorganisms against the viruses is to switch to a dormant, so inactive state, upon contact with the virion, so the virus particles, thus evading infection. There has been some preliminary work in this direction, some experimental studies by Bautista and his co-authors in 2015, and some deterministic dynamical system-based mathematical model by Gurbudak and Weitz in 2016. And both of these works observed that in the early stages, let's say first few hours of the epidemic or the virus infection, a large proportion of individuals switches to dormancy thanks to the contact with the viruses. And our goal is now to study an individual-based and stochastic model for contact-mediated host dormancy, leaving this deterministic setting. We will assume that there's a large amount of active and susceptible individuals that live in equilibrium. And then we ask the question, what happens if a single virus occurs? Now, in the large population limit, we want to determine the asymptotic probability of the emergence of a successful virus invasion and the time until this invasion, if it occurs. And we will observe two phases of a successful invasion. There's an early stochastic phase. Here, randomness plays a prominent role, and here it becomes determine whether the invasion is actually successful. And then the second phase is macroscopic and nearly deterministic. And here, an approximation by systems of ODEs is possible, unlike in the first phase. Let's define the model. We have four types of individuals. Type 1A are the active host cells, type 1D are the dormant host cells, type 1R are the infected ones, and type 2 are the virions, so the free viruses. Now, we fix a carrying capacity parameter k greater than 0, which we will later let tend to infinity. And our population process is a continuous time Markov chain with 4 coordinates, one for each type. And it has values in n0 to the 4, and it has the following transitions. If we have a type 1A individual, so an active individual, this reproduces via clonal haploid asexual reproduction at rate lambda 1 greater than 0, and it dies due to age at rate mu1, where we assume that mu1 is strictly less than lambda 1, so that there's no rapid extinction of type 1A in the absence of viruses. Then virions cannot reproduce on their own, but they can die in a natural way at rate mu2 greater than 0. Now there's competition. Any given type 1A individual dies due to competition with any given type 1A, 1B, or 1I individual at rate c divided by k, where k was the carrying capacity and c is some other positive constant. This leads to logistic competition in the limit k tending to infinity. Let's now define virus attacks. So for any pair consisting of an active individual and the virus, a virion, the virus attack happens at rate d divided by k, where d is some other positive constant. And then with probability 1 minus q, where q is some probability between 0 and 1, the virus attack is successful, and in this case, the host gets infected, type 1I, and the virus, so to speak, dies, but actually it becomes part of this individual, and later this gives potentially rise to further viruses, as you will see. Now with probability Q, the virus attack is unsuccessful because the individual, the active one, gets dormant, and the virus just stays a virus. What is the fate of infected individuals? Either they recover, becoming active and susceptible again. This happens at rate r greater than 0, or they die. This happens at rate v greater than 0. And when they die, they instantaneously give birth to a fixed number m of new virus particles. And this is called lytic virus reproduction. And the number m is called the burst size. What can happen to dormant individuals? Either they resuscitate, so they become active again. This happens at rate sigma greater than 0. And they can also die. This happens at rate kappa times mu1, where mu1 was the death rate for the active individuals, and kappa which is at least 0, this is some scaling parameter for the death rate of dormant individuals. And we know from classical results like Etier and Kurtz that if we fix a finite time horizon t, then if we rescale the population process coordinate-wise by k, then on this compact time interval 0t, it converges in probability to a solution of a 4-dimensional nonlinear dynamical system where we have some quadratic terms coming from the competition terms and the virus attack terms, and all other terms are linear. So now let's study the equilibria of this dynamical system. First of all, 0, 0, 0, 0 is always an equilibrium, but this is always unstable if lambda 1 is greater than mu1. Then there's the so-called virus-free equilibrium where only the active, so type 1a coordinate is non-zero and the other coordinates are 0. And this type 1a coordinate is given as m1a bar equal to lambda 1 minus mu1 divided by c, which comes from logistic competition. Now the question is, does a coordinate-wise positive coexistence equilibrium exist? And this lemma says that the dynamical system has a coordinate-wise positive coexistence equilibrium, which we then call m1a, m1d, m1i, m2, if and only if the following condition holds: u2 times r plus v divided by 1 minus q times d times mv minus r plus v is less than the lambda 1 minus mu1 divided by c, which is just this equilibrium population size m1a bar. And if there is a coexistence equilibrium, then it's also unique. And its active coordinate is precisely given by this expression on the left-hand side of the inequality. Note that this inequality depends only on the dormancy initiation probability Q, not on the death rate scaling kappa or the resuscitation rate sigma of dormant individuals. So only Q is decisive, but for example, when we want to compute the dormant coordinate n1d of the coexistence equilibrium, then it also depends on kappa and sigma. Now, if there is a coexistence equilibrium, then the virus-free equilibrium m1a bar 0, 0, 0 is unstable. If the strict reverse inequality of this inequality holds, then m1a bar 0, 0, 0 is asymptotically stable. Note that n1a, whenever it exists, is less than m1a bar, which means that type 1a really suffers from a persistent epidemic because its population size has been reduced compared to the virus-free case. The effect of dormancy here is that type 1a can maintain higher population sizes without risking a persistent epidemic, because you can see here that m1a bar basically counts only 1 minus q times. So you have to have a higher population size in order to have a persistent epidemic, and this is the advantage of dormancy. Beretta and Kuang in 1998 studied the 3-dimensional variant of this dynamical system where they had no recovery and no dormancy, so r equals q equals 0, and then one can ignore the dormant coordinate. And they showed that if one increases the burst size m, then the system undergoes a single supercritical Hopf bifurcation, which means that this coexistence equilibrium becomes unstable and the solutions converge to a stable periodic trajectory with very high fluctuations. This is actually an analog of the so-called paradox of enrichment, which is known from predator-prey models. Now the analysis of the 4-dimensional dynamical system is more involved, and here we present just some partial results and numerical simulations in this direction. In a nutshell, we conjecture that for small r and q, the behavior is quite similar as in the 3-dimensional case, basically by continuity. And the effect of recovery is that if we choose r large enough, then m1a, m1d, m1i, m2 will remain stable for large m if r is sufficiently large. And the effect of dormancy is that the bifurcation doesn't disappear, but it gets delayed. So you have to choose a larger m in order to see this periodic behavior if q is close to 1. Okay, now here's a numerical example. So if m is, this is a case where r and q are small. If m is equal to 1, then virus reproduction is too bad, and therefore there's no coexistence. The epidemic dies out rapidly. If m is equal to 2, 4, 5, or 7, then we have stable coexistence, but we see that for m equals 2, we have a monotone behavior, coordinate-wise monotone, and then we have an oscillatory convergence to stable coexistence with higher and higher amplitudes. And m equals 12 is already above the Hopf bifurcation point, and here we see that basically we have periodic limiting behavior with very, very high amplitudes. Now let's talk briefly about the first phase of an invasion. If one starts the stochastic process with one virus, then the dynamical system approximation is not immediately applicable because we have no convergence of initial conditions after scaling the population size by k, and therefore we follow an adaptive dynamics approach after the paper of Champagne in 2006, but also we use many concrete techniques by two papers of Koron and her co-authors, and also from some of our previous works with Jochen. And the idea is to show that the resident population stays close to equilibrium until the invaders reach a population size comparable to k. And until this time, we can approximate the invaders by a multi-type branching process. They also may die out, but the approximation is good until they reach a size of order k. And this will be true in the first phase of invasion with high probability. After reaching order k, one can now use the dynamical system approximation, which is good for the second phase. And here, the resident type is type 1a because this starts in equilibrium, and the infected individuals and the viruses are invaders. And classically, one would also think that type 1b, the dormant individuals, these are also invaders because they just emerge thanks to the virus infection. But actually, the dormant coordinate of the branching process turns out to be subcritical on its own, even if the other two coordinates are supercritical. Therefore, our solution is that we also consider type 1d as resident, showing that its population size stays near equilibrium, which is in this case just near 0. Let's define some further objects in order to state our main results. So the largest eigenvalue of the mean matrix of the branching process is called lambda tilde, and then the extinction probability of the branching process is called S2. And S2 is less than 1 if and only if the branching process is supercritical, which turns out to be equivalent to the dynamical system having this coordinate-wise positive coexistence equilibrium. Now, if this coexistence equilibrium exists, then we say that the epidemic has become persistent if the population size process, the stochastic one, divided by k, has reached the persistence set S beta for some small beta. So what is S beta? Here, the sum of the active, dormant, and infected coordinates are less than or equal to n1a bar minus beta. All coordinates are, including n2, at least beta, and there's also some upper bound on n2. Let Ts beta be the hitting time of S beta. Then our first theorem says that the probability of a persistent epidemic is approximately the survival probability 1 minus S2 of the branching process. So assuming that lambda 1 is larger than mu1 and lambda tilde is not equal to 0, and starting from an initial condition when n1a 0 divided by k tends to n1a bar, and we just start with one virus particle and no infected or dormant individuals. For all sufficiently small beta greater than 0, we have that the probability that this hitting time Ts beta is less than infinity, this tends to 1 minus S2 in probability. The other theorem says that the time until reaching the set S beta in case of a successful invasion behaves like 1 divided by lambda tilde log k. So under the assumption that lambda 1 is larger than mu1 and now S2 is less than 1, we have that on the event Ts beta is less than infinity, Ts beta divided by log k tends to 1 divided by lambda tilde in probability, where lambda tilde was the largest eigenvalue of the mean matrix of the branching process. That's what I wanted to say. Thank you very much for listening.